This video is entitled Indeterminate Forms and LHopitals Rule. So we're bringing back the idea of limits. So essentially now we have a section that does not involve integration, so get a little break from that. Now common what we call indeterminate forms when we're evaluating limits is when you get something like 0 divided by 0, either plus and minus infinity over plus and minus infinity, either one of them. 0 times infinity, infinity minus infinity, 1 to the infinity, infinity raised to the 0, and 0 to the 0. Now you might be thinking something, especially a couple of these might look kind of weird to you. 0 times infinity and 1 raised to the infinity. Now we're not saying literally the number 0 times infinity. What we're saying, it's the limit of two things multiplied together where one is approaching 0 while the other one is approaching infinity. So it's not just the number 0 times infinity. And over here, this 1 to the infinity means whatever's in the, so you have an exponent here, of course. So whatever's in the parentheses is approaching 1 while the exponent is approaching infinity. Because your first reaction might be, well, 1 raised to anything is 1, but we're going to see that these problems do not always, well, I mean, sometimes they may have 1 as the answer, but I'm going to show you a famous example where it's not 1. Now here's the theorem for LHopitals Rule. And there's a picture of, that's not me over there, that's LHopital. LHopitals Rule says if you have an indeterminate form, now we do have to do some special stuff with the exponents or whatever to get it into this form, but right now we'll be working with just the division forms, and then the other stuff can be converted. If you take the limit of f of x over g of x as x approaches some value c, and you get an indeterminate form like it's showing you here, 0 over 0 or the infinities, and that, this says that you can then take the derivative of the numerator and the denominator separately and try to evaluate the limit again until you reach something where you either get an answer or you determine it's something where for sure it wouldn't exist. Like maybe you get either infinity as an answer, like say if it was infinity over 2 or something, or you got 3 over 0, like infinity that way. But if you, like say, let's say if you did this, you got 0 over 0, and you took the derivative of the top by itself and the derivative of the bottom, and you got 0 over 0, that means you can apply the rule again. So you can repeatedly apply this rule until you reach a conclusion. So let's see. Let's try this out. Now, sometimes, even if LHopitals Rule applies, we would not want to use LHopitals Rule because it would be very tedious. Earlier ways, like for evaluating infinity limits, you've probably seen where if you had the same leading powers right here, top and bottom, when you go to infinity, you don't care about the smaller powers. You take a ratio of their coefficients. So it'd be 2 over 7. But technically, if you did 5 LHopitals rules, you would get that answer. Now what you would get though is you would not get, you would get a fraction that reduces to 2 over 7. Because you're going to be multiplying top and bottom by 5, top and bottom by 4, by 3. So you're actually going to end up with 2 times 120, which is 240, over 7 times 120 is 840. But that reduces to 2 over 7. So for that one, I wouldn't worry about LHopitals Rule. We can still use some of those basic ideas of how to find limits. Like here's one. Leading power, both square root of x, so we would just take the coefficients 3/5. Now with this one, you have a larger power on top than bottom. On bottom than top, excuse me. Larger power 3/2 versus 1/2 on bottom. That automatically equals 0. Now here's a technique you would have learned. Now I said from Cal 1, of course, at some point in time, if this topic has been moved to Cal 1, just then we'll say from earlier in Cal 1. Some textbooks put this content, LHopitals Rule, in a Cal 1 course, which is fine. but from earlier, some point in time. If you're in Cal 2, it would have been Cal 1. Where the way we would handle this kind of problem, you plug in 2 and you get 0 over 0. So before learning LHopitals Rule, what we would have done is we would have factored the top and bottom, canceled the common factor, reinsert the 2, and you get negative 3 over 2, and the limit would be 3/2. Now, if you did LHopitals Rule, you would take the derivative of the top, which is 2x minus 7, over the derivative of the bottom, which is 2x minus 6, and then you would put in 2, and you get negative 3 over negative 2, so you get 3/2 that way. So that's pretty convenient. Now, another thing from Cal 1 that you might have learned was the limit as sine of x over x as x goes to 0. Now, that's only 0. That is defined to be 1. Now, when I teach this, I always show, either by graphing or table of values or something like that, some method to where, because there's not really an algebraic method for this one. You can't like factor and cancel or anything like that, but you can easily do it graphically or the numerical table of values. But if you did not remember that, it's super easy to get with LHopitals Rule. The derivative of sine is cosine. Derivative of x is 1. Plug in 0. Cosine of 0 is 1. You get 1 over 1, which equals 1. How about that? Let's see. So how about this one? Limit as x goes to infinity of x minus 3 over x squared plus 1. Gives me infinity over infinity. I could do LHopitals Rule, or you could have just looked at the power on the bottom being larger than the top and automatically said 0. That would have been correct. But I want to show LHopitals Rule here. So it'd be 1 over 2x. Then you put infinity in there and you get 1 over infinity, which is 0. Now, I'm making a note here just for illustration purposes. It's not a mathematical requirement when you're doing LHopitals Rule. But I always put like a little asterisk. Maybe I'll come up with some other new symbol in the future. Maybe I should put an L there for LHopitals. But I don't, students are never forced to actually write this. But when I put that star next to a limit, that means I'm applying LHopitals Rule at that point. That's just to prevent me from having to say using LHopitals Rule, over and over and over in the notes, like right there. Star means I'm applying LHopitals Rule. So how about this one? Limit of ln of x cubed over x squared minus 1. You put in 1, you're going to get 0 over 0. So it satisfies LHopitals Rule. Now this first step, I always like to use log properties whenever they apply. You can do this without this step, but it's just instinct for me to do this. To bring that 3 down, makes it 3 ln of x over x squared minus 1. So now I'm going to apply LHopitals Rule. And the derivative of ln of x is 1 over x, so I have 3 times 1 over x. The derivative of the bottom is 2x. You plug in 1 here, you'll get 3/2. And there it is, and I did it in Maple also, so you can see. Now the next example looks similar, but it's not the same. Because this one, you cannot bring the 3 down. The 3 has to stay there. So it's a good review of how to use natural log properties. When the natural log itself is cubed, you cannot bring the exponent down. Alrighty, so that's still 0 over 0 though. If you put 1 in there, you're going to get 0. So you bring the 3 down. So like a chain rule basically. Bring the 3 down. You change the exponent to squared, and then you take the derivative of the inside, which would be 1 over x. So basically it's saying the derivative of u cubed would be 3u squared du, or u prime. So that's all that happened here, but the general power rule, we call that back in Cal 1. So we leave that alone. The bottom's 2x, so now let's put 1 in there and see what happens. We have 2 on the bottom, so that's good, so we don't have the 0 anymore. ln of 1 is 0, so it wipes out everything else, so we get 0 over 2, so we get 0. it's kind of interesting, both of these were 0 over 0. The first one had an answer of 3/2, and the bottom one had an answer of 0. All right, let's see what we got here. Too much purple. Natural log of x squared over e to the x. As x goes to infinity. Infinity squared is infinity. E to the x, well, infinity would be infinity. Take LHopitals rule, my star there, so you have 2x, derivative of the top, over the bottom still ex. That's still infinity over infinity. One more derivative, LHopitals rule, 2x will become 2. Ex is still e to the x. Now you can conclusively say 0 is the answer, because we have a number over infinity. Now we get 0 for sure. All right. Now suppose we switch the numerator and denominator for the previous problem. See, the bottom now will eventually go away, x squared, 2x, then 2. So this is what I was saying, you can keep doing this till you reach some sort of conclusion. It doesn't mean the limit has to have a real number answer. A lot of them will, of course. But here's one where you would just stop, because once you get to ex over 2, it's not the Hopitals rule anymore, and then the answer would just be infinity. Yeah, so say there they are, maple. First one 0, second one infinity. Now this one, the limit as x goes to infinity of e to the negative x. That will always go to 0. E to the x will go to infinity because e to the negative x is 1 over e to the x. So that's just going to go to 0. Or if you reverse this, if you make that e to the positive x, but if you're going toward negative infinity, same rule, just the negatives down here now, you're still going to get 0. So it goes to 0 either way. Okay, let's take a look at this next example. Now you put in 1, because arctan of 1 equals pi over 4, so you end up with 0 over 0. Okay, that means LHopitals rule applies. The derivative of arctan of x is 1 over 1 plus x squared. Of course, remember, pi over 4 is a constant, so the derivative will be 0. And the derivative of x minus 1 will be 1. Now we can insert the 1. So you have the star, meaning LHopitals rule. 1 over 1 plus 1 over 1, 1/2. Now these are good to know. Thinking these might have been used at another part in this book also. But yeah, I might have brought this up at another point, trying to think. Maybe not. But either way, if I did, that's fine. If not, these are good to know. Trig functions, as you go to infinity, really don't tell you too much. Like sine of infinity really doesn't make much sense, or cosine, because it rotates between -1 and 1. But these inverse trigs have interesting results. Actually, if a limit is arctan of x as x goes to infinity is pi over 2, so that's very important to know. Negative infinity would be negative pi over 2. Now, if you forgot these, now of course I put them, an arc secant, same thing. Now if you forgot this, and I put this in degree mode because it's easier to see it in degree mode, then you can always convert it back to radian. But if you were thinking, man, I know that the limit is arctan of infinity, I forgot what it was, but I know it has an answer. I just put in degree mode, I put tan inverse of a big giant number in there, and look what it spit out. Very, very close to 90 degrees. And you can say, oh, 90 degrees, that's pi over 2. And this is something we had earlier on the inverse trig function section in general. When you evaluate, the calculators only have, for now, maybe they'll change later, they only have arc sine, arc cos, and arc tan. But to evaluate arc sec, it's not 1 over arc cosine, it's actually arc cosine of 1 over whatever you're evaluating. So if I put 1 over 99999, I get 90 degrees for that one. So that one's also, and maple says it's pi over 2. So I think there's a good chance I did that correctly by going cosine inverse of 1 over that angle. So how about this one? Now limit x goes to infinity of arctan of x over x squared. Now this one is not LHopitals rule. See, I didn't put a star anywhere. That's what it might be. That's what I'm saying. Arctan of infinity is not infinity, so it's just a number. So all you have here is a number over infinity, so it just goes to 0. Kind of the same rule for this next one. The squeeze theorem basically says that you don't have to really know the formal definition of it, and you can kind of figure this out. Here's how I wrote it. Constant meaning, essentially it's a constant always between -1 and 1, and then you're going towards infinity in the denominator, so that's going to yield a 0. But a more formal way to show it is using this squeeze theorem. And the squeeze theorem says that if you can define your limit between, and the function is between two other limits, and the outside limits have the same result, that means the middle limit has to have the same answer. So in this case, we have, if I put -1 over x minus pi on the outside, and +1 over x minus pi on the other side, and there's no doubt you can clearly see those outside ones go to 0, and there's also no doubt that sine is always between -1 and 1. So the squeeze theorem says if the left one goes to 0 and the right one goes to 0, and we know that this one's always between them, of course it can touch them. That's why it has the equals there. Then the middle part has to go to 0. So that's all the squeeze theorem's basically telling you. Works well for weird stuff like with limits involving sine and cosine. I don't see you being tested directly on that. All right. As x goes to 0, we've got limit of x over arctan of 2x, which that's going to give you 0 over 0, so that does apply as the Hopitals rule. So you take the derivative of the top, which is 1. The derivative of arctan is basically u prime over 1 plus u squared. So the derivative of 2x is 2 over 1 plus 2x all squared, so it's 4x squared. Now you can plug the 0 in there. So that's going to get 1 right there. So you basically just have 1 over 2. So it's 1/2. There you go. Here's limit as x goes to infinity of ln of x to the 4th over x cubed. I bring the 4 down. So that's definitely infinity over infinity. So it's 4 ln of x over x cubed, still infinity over infinity. And then one more in Hopitals rule will give you 4 times 1 over x over 3x squared. You drop the x down. Now you can clearly say it's 0. So I'm mentioning here that the limit as x goes to infinity of ln of x is equaling infinity. But it's a very slow process. It is not in a hurry to get to infinity. X is obviously climbing way higher. I just put this in Maple. Look, as I put this gigantic number in here with a 1 and a whole bunch of zeros of ln of x, and it came up with this, and I just converted it to decimal. So that was only 140 right there. But it is increasing. You see, it's increasing as I increase the value, but it's just super, super slow. But it's heading to infinity. But it's in no hurry. So yes, ln, but whereas on the other hand, e to the x is like a rocket ship to infinity. It's really taken off. All right, so let's see what we have here. Next one. Oh, I kind of brought back something back from Cal 1, just as probably, I shouldn't say, I guess I could reserve the right to put that on a test at some point in time, but at the time of this recording, I certainly don't plan on doing it. But this is something that's back from Cal 1 called, well, at least in this book, it's called the second fundamental theorem of calculus. So it might not be called that if you're used to studying from a different textbook. But anyway, long story short, you put 1 in here, the plus isn't going to matter here. It just means that the plus means it has to come from the right. But anyway, if the upper and lower limits are both the same, that means that's going to be 0. And over x minus 1, you put 1 in there, you're going to get 0. Now technically, okay, so this is going to the second fundamental theorem of calculus says that when you're taking the derivative of an integral, all you have to do is take, assuming the lower limit's a number, you take that upper limit, this case is the x, you substitute it for the theta, and then you take the derivative of whatever that upper limit is. So in this case, the derivative of x is 1. So let's just say if that would have been x squared instead of x. We would have had cosine of x squared and then times 2x right here. That would have been a 2x because the derivative of x squared is 2x. And then that's the one L'Hopitals rule, and you put 1 in there, so you just have cosine of 1 radian, whatever that is. I put this in maple. I have no idea why I used omega as a variable instead of theta. It made no difference mathematically. I don't know why I did that. Maybe I just clicked on the first variable that I saw. But it's correct, so yes, that's called the second, often called the second fundamental theorem of calculus. All right, how about this one? ln of x over sine of pi x. That's going to be 0 over 0 because you put 1 in there. ln of 1 is 0. Sine of 1 pi is 0. So it does satisfy L'Hopitals rule. The derivative of the top will be 1 over x. You've got to be real careful here not to make a mistake. See, a lot of people do this. It would be really easy to say that the derivative of sine pi of x is just cosine of pi x. But because of the chain rule, it's pi cosine of pi x, meaning we have to take the derivative of the pi x part. Yes, and that would totally affect this answer. Now you insert the 1. You get 1 over 1. Now you cosine of pi right here, which makes negative 1. So in other words, it's really, okay, 1 over negative pi is the same thing as negative 1 over pi. Same thing. And maple says negative 1 over pi, so that's always good. Anytime we match maple, that's always a good thing. Let's see what's next here. Oh. I think I erased something here. Must have erased this by accident. And let me put this in here real quick. See if I can copy that. So next one is 1 minus cos of 5x over 3x squared. Sometimes I probably get a little sloppy dragging my cursor around and not realize I've erased something. 0 over 0 when you put that in there, so L'Hopital applies. The derivative of negative cosine would actually be positive sine. Then the derivative of 5x is 5, so just kind of like that last one. Chain rule applies, so I'm kind of glad I did another one of those. All right. So put in 0, you get 0, and you get 0 over 0. So guess what? L'Hopitals applies again. So the next derivative would make that 25 cosine of 5x. And the derivative of 6x will be 6. You put in 0. Cosine of 0 is 1. So you have 25 over 6. All right, so very good. Let's look at this next one. This next one is a little bit messy. I did it a couple of different ways here. You know, this one's a little more challenging, I guess you might say, but a couple of ways you can go about this one. I kind of did it without L'Hopitals rule, actually. Well, I did one step of L'Hopitals rule. So anyway, without further ado, here we go. Limit as x goes to 0, positive tan of x minus x over x cubed. That's definitely 0 over 0. L'Hopital's rule. The derivative of tangent is sec squared. Derivative of minus x is minus 1 divided by 3x squared. Now that is 0 over 0. So technically, you could proceed with L'Hopital's rule. Again, mathematically, that would be right because you're in a correct form for L'Hopital's rule. But I chose a different route. Mainly because we're approaching 0 here, and you'll see the plus doesn't matter. In this case, it doesn't. So we have tan squared, I rewrote it as sine squared over cos squared over 3x squared. Now, unlike limits have interesting properties, unlike derivatives. Derivatives you can't, the derivative of f times g is not f prime g prime. You can't split them up. With limits, you can. In other words, the limit of, let's say, f times g times h would be the limit of f times the limit of g times the limit of h. But you can't do that with derivatives. So what I did is I kind of used this thing. I showed this earlier using L'Hopital's rule. So let me scroll back up here just for a second. But knowing that, of course, you can derive it, of course, but knowing that this limit equals 1 is what is going to really help us in this problem. So I split this up. So I had a couple of sine squares. I got cosine squared on bottom. So I took a sine x with an x, paired it up. Took another sine x with an x, paired those up. Now this 3, I could have left it somewhere, but I brought it to the outside, made it 1/3. But I did this because you see I crossed those two out. By definition, those are automatically 1, or by value, they already have a value of 1. Now the next one, you actually shouldn't have crossed it out probably because you actually evaluate this one, but this is 1, this is 1. Then actually, so you're left with a cosine squared and nothing else but a 1 on top. But now you plug the 0 in. So this isn't an identity or rule here. This is just literally evaluating it. You put 0 in there. Cosine of 0 is 1. 1 squared is 1. You get 1. So actually, you just end up with this 1/3 on the outside times a bunch of 1s, and you get 1/3. Now the other approach would be starting with where I took the first L'Hopital's rule. So I took that same starting point right there and went ahead and did L'Hopital's rule. Got to be real careful with this derivative if you do it that way. You're essentially taking the derivative of u squared. U squared would be 2u du. So the 2 comes down right here. Secant exponent becomes a 1. And the derivative of secant is secant tangent over 6x. That's 0 over 0. But you see, I still went ahead and went sine and cosine this way too. I still went ahead and did that. Because if you keep doing L'Hopital's rule, sometimes things could get kind of bad on this one. I mean, I don't know. Technically, it satisfies L'Hopital's rule, but you can see right here, that's going to be a product rule in the denominator, so I don't know how that's going to help much. Although we would have been able to factor out a cosine after we did, because I had cosine here, and I would have had a two different cosines there. So maybe one day I'll go back and try to do that with another L'Hopital's rule and see if it would have got simplified or not. It might have worked out all right. I just thought it was going to be bad because of the product rule, but it might not be. Actually, I guess it wouldn't, because I'm going to write this real sloppy for a second on the other page. So the numerator would be cos, and in the bottom, if it was x cos cubed, x cos cubed. So if I go if I go f prime first, that'll be 1. So that'd be cos cubed, and then plus x times this derivative, which will bring a 3 cos squared x, and then the derivative of cosine would be negative sine of x. If I factored out then a cosine on the bottom, I'd be left with cos squared minus 3 sine x cos x. So obviously this cos x would cancel with that cos x. That's cos x on the bottom. And let me just double check that we are going to 0 here. As x approaches 0. And, oh, I forgot the 1/3. So there was the 1/3 factored out of here. All right, let me double. Yeah, there was this 1/3 here. So you put 0 in here. Okay, that wouldn't have been so bad, I guess, as long as you didn't mess up this derivative. You put 0, you get a 1 right there. Sine of 0 is 0, so it wipes out all this. So you have 1 over 1 with the 1/3 in front, and that would have made it 1/3. All right, so maybe I should have taken that extra step. Oh, well, that's all right. Now, the next kind of indeterminate form, 0 times infinity. So once again, that does not mean literally the number 0. It means one part is approaching 0 while another part's approaching infinity. Now what you have to do on this one is drop one of the two down to the denominator. Because you drop one of the two down, if you drop the 0 down, that makes it infinity over infinity because you're then dividing by 0. If you drop the infinity down, that would make it 0 over 0. So it gets it, because dividing by infinity is 0. So that gets it 0 over 0 or infinity over infinity, with one very important rule here. Sometimes it's tricky with trig functions, and these two will be a primary example of that. But one thing we will not ever do is drop natural log to the denominator. But otherwise, there's no really set rules, so you have to be careful. But well, the good news is if you try one method and it seems to be getting worse and worse and worse, then go back and change it to drop the other term down in the bottom, unless it was natural log, and then we don't do that. Now this one, x cubed, I dropped the cotangent. Obviously the reciprocal which obviously you could write when you divide 1 over cotangent, but cotangent becomes tangent on the bottom. So I rewrote this as x cubed over tan x, and it now puts it in LHopitals Rule form. And we have the derivative be 3x squared over sec squared of x. Now you put in 0, you'll get 0 over 1, so you'll get 0. So like I said, here's an example. Like I said, the first one you'll drop the trig one, the next one you'll drop the other one. But like I said, if you mess this up and it looks like it's getting really, really bad, go back and change which one you're dropping. But you got to be careful. Now this one, because that's the tangent's the reciprocal of cosine. Cotangent, excuse me. Those are reciprocals. Now when I'm dropping the x this time, but I can't put x on the bottom, I have to put 1 over x. Because think about it, because dividing by 1 over x is the same thing as multiplying by x. So obviously, however I rewrite this has to be equivalent to the original function. So when you drop something that's not a fraction, it becomes 1 over whatever that is. Now this is kind of interesting. The derivative of tangent of 1 over x is going to be secant squared 1 over x times 1 over x prime. Now I didn't take the derivative at this step. I could have, but I did not, because I saw what was going to happen on the bottom. And if you did, it'd be okay, but it makes it a lot quicker. But so then you're taking the derivative of the bottom, which is 1 over x prime. So what I notice is, since they're without taking the derivatives, I know that they're both going to be 1 over x primed right there. So they just cancel them. But yeah, you could take them as derivatives and then cancel them. But that was a much quicker way to cancel them before even taking the derivative. Now I insert infinity. So you look at this as 1 over infinity. It's basically going to 0. Secant squared is 1 over cos squared. Secant and cosine of 0 both go to 1. So secant of 0 is 1, therefore 1 squared is 1. So it all goes to 1. And there are the two maple answers for that one. Very good. So how about this one? X times ln of x. We do not drop the ln of x, so we have to drop the x. So dropping the x, I'm just showing it's 0. So actually, as you're approaching, and this time the plus has to be there strictly. Earlier we did a problem, I said it didn't matter. But this one definitely matters, just strictly for the fact is, the only way that you can approach 0 in a natural log function is coming from positive to like that direction. Because log is undefined on the other side of 0. So there it doesn't affect the answer, but here it has more of a precise meaning on why it needs to be done. Anyway, that's heading toward negative infinity. That's okay. 0 times infinity, 0, negative infinity. I just sort of showed that here in case you didn't believe me or maybe whatever, but it's very slow, but as I started making them smaller and smaller and smaller, see the negatives are increasing, aren't they, or decreasing, I should say. Yeah, so that's anyway. We take the derivative of ln of x is 1 over x. The derivative of 1 over x is negative 1 over x squared. Flip-flop all that around. You get negative x. Put the 0 in, you get 0. So that one turned out being 0. Now the next case, if you have a situation where it's the form infinity minus infinity, you've got to merge it into one fraction and then do LHopitals Rule. Both of these would be infinity results separately. But okay, this one's nice because it already has a common denominator for us. So I merged it into one fraction without not any work because it's the same denominator. That's definitely 0 over 0. If you put 2 in there, you get 0 on top. You put 2, you get 0 on bottom. Do LHopitals Rule. Bring the 1/2 down, so it'll be negative 1/2. X minus 1 to the negative 1/2. Derivative of the inside chain rule will be 1. Over the derivative of the bottom, x squared minus 4 will be 2x. And if you plug 2 in here, 2 minus 1, so that's basically 1 to the anything, so is 1. 1 to the negative 1/2, that makes that 1. So you're left with negative 1/2 over 4, which gives you negative 1/8. And Maple says that, so that's good right there. Probably right here. Now we're looking at the 3 indeterminate forms where we have exponents. Now if you look at this one, that's what I was telling you earlier. So this is, as we put infinity in there, 1 over infinity goes to 0. So you basically have 1 plus 0 is 1. And then, of course, x is heading to infinity. So the inside's approaching 1 as x approaches infinity. So it's not really 1 to the infinity. So it's not like you can automatically say, well, the answer is 1, game over. Yeah, sometimes it might be 1. This one is not going to be 1. So it really makes it interesting. So here's how you have to handle these kind of problems. You've got to define this limit as some sort of variable name. The choice of y is completely irrelevant. You could put a happy face there if you wanted to. It wouldn't matter. Just needs some kind of symbol to represent as the limit as a variable. Because what we're going to do is we're going to take the natural log of both sides of this equation. So we take the natural log, and that's going to allow our exponent to come down. So you take the ln of both sides. Now here's an interesting property, and you'll be able to save some steps on this once you realize this in the future. You take the ln, you can go ahead and put the ln on the inside if you want to, but I didn't want to do that for the very first problem. But anyway, I took a little extra care on this one. You can kind of do it all in one step if you want to, but natural log of a limit is the same thing as the limit of the natural log. And then that enables the x to come down. So, whenever you feel comfortable, you can, realize what you have there, that you can put the ln in there and then bring your exponent down in front of it. Now, this part you get right here after you do that, and we can leave the left side alone for a while. Worry about that later. We're just working with the right side. So now you're always going to be left with something that represents infinity times 0. Now this will be a lot easier to choose what to do, because since this is always going to have a natural log, because you're using natural log, you're always going to have infinity times 0. And then you're always going to, you're going to bring the part that's not ln down. So there's no question. We do not bring natural log down to the denominator. So we bring the x down to make that 1 over x. So notice I kind of left the left side alone. We know the ln of y. We come back in there. We'll deal with that in a minute. So now I'm applying LHopitals rule to this right here. So the derivative of natural log basically is u prime over u. So it's the derivative of the inside over the inside. So I kind of wrote it as a derivative. 1 plus 1 over x prime over 1 over x, and the bottom's 1 over x prime. Now I canceled these two out again. I found a little shortcut there again. I canceled those out. But why could I do that? Because they're not the exact same looking things algebraically, and that's true. But if you think about it, their derivatives would be the same. That's all that matters. I'm canceling the derivatives. The derivative of 1 plus 1 over x is the exact same thing as the derivative of 1 over x, because the derivative of 1 is 0. So that part wouldn't make any difference. So, okay. So even though they didn't look the same, their derivatives still cancel. And now I rewrite it like this. I put infinity in there. So I have 1 over 1 plus 1 over infinity. That's 0. So I have 1. So you might think, see, I told you so. The answer was going to be 1. But that's not the answer. There's always one very important step you have to do here at the end. What we got for 1 is, remember, we defined our original limit as y. But what actually equals 1 is ln of y is what equals 1, not y itself. So we just found out basically that ln of y equals 1. So the last step in this process every time is to raise e on the both sides. Well, mainly the right side. Just the left side is just there to knock out the ln. So you have to e both sides, like right here. Then that gets it back to y, because y is what your limit essentially is. So the y is the original limit. So now we're saying it's e to the 1, which is e. So that actually equaled e. In fact, I didn't mention this before. There, Maple has it. I didn't mention this when I started this problem, but that is one of the definitions for e. The limit as x goes to infinity of 1 plus 1 over x to the x. Now, you might have seen that in the exponential sections. I don't know if I mentioned that, hey, we'll be able to prove that this equals e later. I usually do that in a face-to-face class. I'll say, guess what? We're going to show that this is e. And it is. It's e. We proved it. Okay, so we have to remember to go e to whatever the exponent is. How about this next one? This one qualifies. Now, actually, if you had 0 raised to an infinity, that would just be 0. It would not be one of those. We're basically looking for the following three here. 1 to the infinity, infinity to the 0, and 0 to the 0. I would not put 0 to an infinity on a test, but I just wanted to mention that just from a general limit standpoint. Infinity to the 0. So we got to put the variable y or whatever letter you like to define your limit. So now I kind of did a couple of steps at once, like I explained in the last problem. Yeah, we ln both sides, but I went ahead and just imagine if I put ln, then I moved ln to the inside and brought 1 over x down to get this. And that's absolutely correct. So you can do that, or if you'd rather take more steps, that's totally up to you. I want to see if I can put some sort of bracket around here, freehand one. Doesn't matter, but Yeah, so you can kind of save yourself a couple of steps of writing there if you want. Okay. Well, ln of x never drops down, so guess what? Well, actually, the 1 over x means, so that means it's already x on the bottom, so that's good. So obviously, if it was x here, it becomes 1 over x on bottom, but 1 over x just means the x is there. So now we have this, limit as x goes to infinity, ln of 1 plus x over x. So LHopitals rule is going to apply here. So the derivative of ln of 1 plus x would be the derivative of 1 plus x, which is 1 over 1 plus x. The bottom is going to be 1. And now you put the infinity in there, you're going to get 1 over infinity, which is 0, over 1, which is 0, but 0 is not the answer. We e both sides. E to the 0 is the answer. And e to the 0 will be 1. So you can see I put the original limit back in here and got 1. So don't forget to e that last step. So how about x to the x? I'm making sure I'm covering all these terms here. This covers the 0 to the 0. So I'm going to ln both sides. That means I'm going to put the log in front of this. The x comes down, so you have ln of x ln of x. I drop the x down to make it 1 over x. I apply the Hopitals rule, so I'll get 1 over x over negative 1 over x squared. And then flip-flop around, that ends up being negative x. I think we had one like this a little while ago. And you put 0 in there, you get 0, but 0 is not the answer. It's going to be e to the 0, which will be 1. And there I have the answer right there in Maple. There's another 0 to the 0 involving a trig function. So that looks like fun. Sine of x raised to the x is 0 to the 0. Bring the x down. We put an ln in there, basically. ln both sides. Bring the x down, so you have the limit of x times ln of sine of x. And we drop the x down to make it 1 over x on the bottom. And then we'll do LHopitals rule. So the derivative of natural log of sine of x will be the derivative of sine of x, which is cosine over sine, and then the 1 over x will be negative 1 over x squared. So I flipped it, the fraction divided by fraction, flip it over. I pulled the negative to the outside. That wasn't necessary. I could have left the negative in there. So I left with this mess here, which technically is 0 over 0, but one thing on the property I didn't mention earlier, I do in count 1, of course, but when we're learning this, but we saw the limit as x goes to 0 of sine of x over x equals 1. Well, it's also true if it's x over sine of x. Either way, either fraction, reciprocal, they're both 1. So I just kind of made this a little simpler by taking away an x and taking away a sine. That goes to 1. Then I was left with 1 more x. The negative's still there, just in case. And then I was left with cosine of x, but we actually won't need the negative here, because as soon as you put 0 in there for your x, that makes everything 0, so we'll do that negative. So we have 0, which will be e to the 0, which will be 1. So you see Maple says that equals 1. How about this one? Limit as x goes to 0 of e to the x plus x raised to the 2 over x. That's going to bring back 1 over infinity. It'll be that form. So we're going to ln both sides. Kind of skipped a couple steps there. Well, yeah, that's all right. When you bring the 2 over x down, that's obviously putting the x in the denominator. So that's already, that x right there is coming down right here. The 2 can stay or go to the, I just left the 2 here. And, oh, well, I didn't have to mathematically do this, but just for the reader's benefit, I forgot my star there, didn't I? But I was doing Hopitals rule. So we have, it'll be the derivative of e to the x plus x, which will be e to the x plus 1, over e to the x plus x. The 2 just stays there. The derivative of x is 1, so now I just kind of drop this fraction back down to the denominator. So I have this. I put 0 in there. So on the top, I'm going to get e to the 0, which is 1. 1 plus 1 is 2. 2 times 2 is 4. On the bottom, I get e to the 0, which is 1 plus 0, so I just get 1. So it's 4 over 1. So we get 4, but remember 4 is not y, it's ln of y. So we have to e both sides. And then we have e to the 4. So y equals e to the 4, and there it is in Maple. The next one falls under the infinity to the 0 category. So actually we ln of an ln here. So the 2 over x comes down. We have ln of x, which is fine. The x goes to the bottom. And forgot my star again. So I'm taking the derivative of ln of x. And we have so the derivative of ln of x will be the derivative of ln of x divided by ln of x. So the derivative of ln of x is 1 over x divided by ln of x. That's 1 on the bottom. So I drop the ln of x down. Both the x and the ln of x go down. 2 stays up. So I put in infinity. I definitely have 2 over infinity, so that goes to 0. And that means y equals e to the 0, which is, of course, is 1. And Maple has 1 for that one, so that's good. And the last thing I had in here, I found this on Googled this somewhere. Somebody asked about it. You're not responsible in my class for having to memorize or know that, but there's a proof of LHopitals Rule. You want to see how it really works. So that concludes the video on indeterminate forms and LHopitals.